Tonight we're going to take a journey to the nearest star system beyond our own, Alpha Centauri. It's sitting there in the southern sky, about 25 trillion miles away. And we're going to figure out what it would actually take to get there. Not just the physics or the engineering, but the reality of what such a journey would mean for anyone who attempted it. Because here's the thing most people don't realize. Getting to Alpha Centauri isn't just difficult. It's not just a matter of building a bigger rocket or waiting for better technology. It's something far more extreme than that. The journey to our nearest stellar neighbour would be one of the most terrifying undertakings in human history. And by the end of tonight, you're going to understand exactly why. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what you think you know about Alpha Centauri. You've probably heard it's the closest star to us. That's not quite accurate, but it's close enough for most purposes. Alpha Centauri is actually a triple star system, 3 stars bound together by gravity, located about 4.37 light-years away. That's roughly 25.6 trillion miles or 41 trillion kilometers. In cosmic terms, this is our next-door neighbor. The 3 stars are designated Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and B are sun-like stars that orbit each other, while Proxima Centauri is a small red dwarf that orbits both of them at a much greater distance. Proxima is actually the closest of the 3 to us at 4.2424 light-years away, which is why it's called Proxima, meaning nearest in Latin. In 2016, astronomers discovered a planet orbiting Proxima Centauri. They named it Proxima Centauri b, and it's roughly Earth-sized, orbiting in what might be the habitable zone where liquid water could exist on its surface. This discovery made Alpha Centauri even more interesting as a potential target for interstellar exploration. We might not just be visiting another star system. We might be visiting a world where life could exist. But before we get too excited about potential alien life, we need to confront the reality of the journey itself. 4.2424 light-years doesn't sound that far. A light-year is the distance light travels in 1 year. And light is the fastest thing in the universe, moving at about 186,000 ms or 300,000 km. Light from Proxima Centauri takes 4.24 years to reach Earth. That means when you look at Proxima Centauri through a telescope, you're seeing it as it was 4.24 years ago. The light left that star over 4 years before it hit your eye. So, if light can make the trip in 4.24 years, how long would it take us? Here's where things get uncomfortable. The fastest spacecraft humanity has ever built is the Parker Solar Probe, launched in 2018 to study the Sun. At its peak speed, the Parker Solar Probe reaches about 430,000 mph or about 692,000 km per hour. That's unbelievably fast by human standards. At that speed, you could travel from New York to Los Angeles in about 6 seconds, but in cosmic terms, it's painfully slow. If the Parker Solar Probe were pointed toward Proxima Centauri, which it's not, it would take about 600-700 years to get there. Think about that for a second. 600-700 years. The entire span of recorded human history is only about 5000 years. Our fastest spacecraft would take longer to reach the nearest star than all of human civilization has existed. And that assumes the spacecraft could maintain its speed. which it can't. The Parker Solar Probe achieves its incredible velocity by falling toward the Sun and using gravity assists out in interstellar space far from any massive body. It would slow down. You'd need constant propulsion to maintain speed, which requires fuel, and fuel is heavy, and carrying heavy fuel requires more fuel to accelerate that mass, and you quickly run into a fundamental problem of rocket science. So, let's say we want to get there faster. What would it take? The conventional rockets we use today, even our best chemical rockets, can't do it. They're just too slow to make the journey in a human lifetime. You'd need to travel at a significant fraction of the speed of light, and nothing we've built or even designed can come close to that. There are theoretical propulsion systems that might work. Nuclear pulse propulsion, where you detonate nuclear bombs behind your spacecraft and ride the shock wave. Fusion drives that combine hydrogen atoms to release energy. Antimatter engines that annihilate matter and antimatter to produce thrust. Ion drives that accelerate charged particles to very high speeds. Solar sails pushed by light from stars or powerful lasers. Each of these has problems. Nuclear pulse propulsion was seriously studied in the 1950s and 60s under Project Orion. The idea was simple in concept. Drop nuclear bombs out the back of your spacecraft, detonate them and absorb the blast with a massive shock absorber plate. Computer simulations suggested this could work, potentially accelerating a spacecraft to several % of light speed. But there are obvious issues. You'd need thousands of nuclear weapons. The radiation would be intense. The engineering challenges are enormous. And launching such a spacecraft from Earth would be politically and practically impossible. Fusion drives sound promising. The Sun runs on fusion, combining hydrogen atoms into helium and releasing energy in the process. If we could harness that reaction in a controlled way, we could theoretically build an engine with incredible efficiency. The fuel hydrogen is the most abundant element in the universe. But we haven't achieved controlled fusion yet. Not in a power plant on Earth, and certainly not in a compact form suitable for a spacecraft engine. Researchers have been working on fusion for over 70 years, and we're still not there. Even optimistic projections suggest we're decades away from a practical fusion reactor, let alone a fusion rocket. Antimatter engines are even more speculative. When matter and antimatter meet, they annihilate each other completely, converting all their mass into energy. According to Einstein's famous equation, E equals sine mc22, this is the most efficient energy release possible. A tiny amount of antimatter could in principle provide enormous thrust. The problem is producing and storing antimatter. We can make it in particle accelerators, but only in microscopic quantities. The total amount of antimatter ever produced on Earth would barely power a light bulb for a few minutes. Scaling up to the kg or tons you'd need for an interstellar journey is nowhere near our current capabilities. And even if you had the antimatter, storing it is nearly impossible. It can't touch any ordinary matter, or it would immediately annihilate. You'd need magnetic containment systems that could hold it perfectly for years or decades without any failure. 1. Malfunction and your fuel supply explodes. Releasing more energy than a nuclear weapon, ion drives are real technology. We've used them on spacecraft like Dawn and Deep Space One. They work by ionizing a gas, usually xenon, and accelerating the ions with electric fields. The thrust is tiny, but because they're so efficient, they can run for years, gradually building up speed. The problem is that gradual acceleration takes time. Ion drives are great for missions within the solar system, but for interstellar travel, you'd need to run them continuously for decades, just to reach a fraction of a % of light speed. and you'd need enormous power, probably from nuclear reactors, which adds mass, which requires more thrust, which requires more fuel. Solar sails are elegant in concept. Light carries momentum. When photons from the sun hit a reflective surface, they transfer that momentum, producing a tiny push. If you built a large enough sail, lightweight and reflective, the sun could push it to significant speeds. The Japanese spacecraft 330S demonstrated this technology in 2010. A solar sail could theoretically accelerate indefinitely as long as there's light hit in it. The problem is that light pressure is incredibly weak. To get any useful acceleration, you need a sail that's enormous, potentially square kilometers in area, but also incredibly light, just a few G per square meter. Building such a structure is a massive engineering challenge. And even if you could build it, the sun's light weakens rapidly as you move away. By the time you are out past the orbit of Mars, the light pressure is so weak that acceleration becomes negligible. One proposed solution is to use a ground-based or space-based laser array to beam concentrated light at the sail. The Breakthrough Starshot initiative announced in 2016 proposes exactly this. The idea is to build a massive laser array on Earth or in Earth orbit and use it to push a tiny spacecraft equipped with a lightweight sail. The spacecraft would be about the size of a microchip, weighing only a gram or so, with a sail a few meters across. The laser would hit the sail for a few minutes, accelerating the craft to about 20% the speed of light. At that speed, it could reach Alpha Centauri in about 20 years. This sounds promising, but there are significant challenges. First, the laser array would need to be incredibly powerful, probably gigawatt or more. That's the output of a large power plant, and all that energy would need to be focused precisely on a tiny sail that's already moving away from Earth at thousands of kilometers. The precision required is staggering. Any misalignment and the laser misses the sail entirely. Second, the spacecraft is so small that it couldn't carry much instrumentation. A few cameras, maybe some basic sensors, but nothing sophisticated. It couldn't carry enough power to transmit data back to Earth, at least not at any reasonable rate. You might get a few images, a handful of measurements, and that's it. Third, once the spacecraft is accelerating, there's no way to slow down. It would scream past Proxima Centauri at 20% light speed, giving it only a few hours, maybe less, to observe and transmit data before it's gone, flying off into the depths of space forever. And fourth, even at 20% light speed, communication would be a problem. The spacecraft would be over 4 light-years away. Any signal it sends would take 4 years to reach Earth. By the time we receive the data, the spacecraft would be long gone, and if something went wrong, we'd have no way to fix it. So, even the most optimistic proposals for interstellar travel involve serious compromises. But let's imagine we solve all these problems. Let's say we develop a propulsion system that can accelerate a crewed spacecraft to 10% of light speed. That's still 40 times faster than our fastest current spacecraft. But it's within the realm of theoretical possibility. At 10% light speed, the journey to Proxima Centauri would take about 42 years. That's the travel time. One way, now, we need to think about what that means for the crew. 42 years is a significant portion of a human lifetime. If you launched at age 30, you'd arrive at age 72. You'd spend your entire adult life on a spacecraft, never setting foot on solid ground, never breathing fresh air, never seeing a natural horizon. And that's assuming everything goes perfectly. Let's talk about what life would be like on such a journey. First, the spacecraft would need to be large enough to support a crew for Decades. You'd need living quarters, workspaces, life support systems, food and water supplies, medical facilities, exercise equipment, and probably recreational areas to maintain mental health. The crew would need to be self-sufficient. There would be no resupply missions, no help from Earth if something breaks. Everything they need for 42 years would have to be on board from the start, or they'd have to manufacture it themselves from raw materials. This means the spacecraft would need to be large, probably several hundred meters long, possibly more. It would need to be a self-contained world, a tiny island of Earth flying through the void. The crew size is a critical question. Too few people and you run into genetic problems if you're planning a multi-generational journey, or you lack the expertise to handle every possible emergency. Too many people and you need more space, more food, more water, more air, and the spacecraft becomes prohibitively massive. Most studies suggest a minimum crew of several 100 to 1,000 people for a multi-generational mission, though a shorter journey might get by with fewer. For a 42-year journey, you might manage with 50 to 100 people, assuming they're all experts in critical fields like medicine, engineering, biology, and psychology. These people would need to work together in a confined space for over 4 decades without any possibility of leaving. The psychological challenges would be immense. Humans evolved to live in open environments with variety and change. Being locked in a metal box for decades, seeing the same faces, walking the same corridors, eating the same recycled food, it would test anyone's sanity. Studies of isolated environments like Antarctic research stations, submarines, and the International Space Station give us some idea of what to expect. Even in these relatively short-term missions lasting months to a year or two, people experience depression, anxiety, interpersonal conflicts, and decreased cognitive function. Now multiply that stress by decades. You'd need careful crew selection, rigorous psychological screening, strong social structures, and probably professional counselors as part of the crew. Even then, conflicts would arise. Romances, jealousies, personality clashes, political disagreements, all the normal human drama, but with no escape. No way to get away from the people you're arguing with. In extreme cases, you might have violence, mental breakdowns, even suicides. Mission planners would need to prepare for these possibilities, which is a grim calculation. Then there's the physical environment. The spacecraft would be in free fall for most of the journey. Weightlessness causes bone loss, muscle atrophy, fluid shifts, vision problems, and immune system changes. Astronauts on the International Space Station exercise for hours every day to counteract these effects. And even then, they experience significant deterioration after just 6 months. For a 42-year journey, you'd need artificial gravity. The most practical way to create artificial gravity is through rotation. Spin the spacecraft and centrifugal force pushes everything toward the outer hull, simulating gravity. But this introduces engineering complications. The spacecraft would need to be designed as a rotating cylinder or torus. The rotation rate has to be just right. Too slow and the gravity is too weak. Too fast and the Coriolis effect becomes problematic. The Coriolis effect is what happens when you move in a rotating reference frame. If you walk perpendicular to the direction of spin, you feel a sideways force. This can cause nausea and disorientation. Studies suggest you need a rotation radius of at least 100 m to keep Coriolis effects tolerable, which means the spacecraft needs to be large. Very large. Power is another critical issue. You'd need enormous amounts of power for life support, propulsion, lighting, computers, communication, and everything else. Solar panels won't work. Once you're beyond the orbit of Mars, sunlight is too weak. By the time you're even a fraction of the way to Alpha Centauri, the sun is just another star, providing negligible energy. You'd need nuclear reactors, probably multiple reactors for redundancy in case one fails. These reactors would need to operate continuously for decades, without maintenance beyond what the crew can perform. The fuel would need to last the entire journey, or you'd need to carry spare fuel rods, which adds mass, and nuclear reactors produce heat in space. Getting rid of waste heat is surprisingly difficult because there's no air to carry it away. You need radiators, large panels that emit infrared radiation to shed heat. The larger and more powerful your reactors, the more radiators you need, and radiators are heavy and vulnerable to damage. Food and water are perhaps the most fundamental challenges. You can't carry 42 years' worth of food for 100 people. The mass would be astronomical. You'd need a closed-loop life support system. This means recycling everything, water from washing, from urine, from the air, all of it filtered, purified, and reused. The International Space Station already does this, recycling about 93% of water. You'd need to push that efficiency even higher, closer to 100%, because any loss accumulates over decades. Food would need to be grown on board. You'd need hydroponic or aeroponic gardens, growing plants under artificial light. Plants would also help recycle carbon dioxide into oxygen, supporting the life support system. But growing enough food for 100 people requires significant space and energy. The plants need light, water, nutrients, and careful monitoring. Crop failures could be catastrophic. You'd need backups, seed banks, multiple growing chambers in case one gets contaminated or fails. Meat would be a luxury, probably limited to lab-grown cultures, if it's available at all. Most of the diet would be vegetables, grains, and maybe fish from aquaculture tanks. Variety would be limited. After a few years, the crew would know every meal by heart. Medical care is another concern. People get sick, injured, develop chronic conditions. On Earth, you go to a hospital. On an interstellar spacecraft, you are the hospital. The crew would need at least one doctor, probably several, along with a well-stocked medical bay. But what happens if someone needs surgery for appendicitis, a broken bone, or cancer? The crew would have to handle it with whatever equipment and supplies they brought. Advanced imaging like MRI might not be available because of the mass and power requirements. Pharmaceutical supplies would be limited. Some medications degrade over time, losing potency. You'd need to manufacture some drugs on board or carry enormous stockpiles. And what about aging if the crew is in their 30s when they launch? They'll be in their 70s when they arrive. They'll experience all the health problems of aging. Heart disease, arthritis, dementia, vision and hearing loss. Some crew members won't make it to the end of the journey. That's statistically certain for a 42-year voyage. The spacecraft would need facilities for handling the deceased. Probably some form of burial in space or storage in a designated area. This is grim to think about, but it's a reality mission planners would have to face. Now, let's talk about the dangers of the journey itself. Space is not empty. There's gas, dust, and the occasional rock. At normal spacecraft speeds, hitting a grain of sand isn't a big deal. At 10% the speed of light, it's like being hit by a bomb. Kinetic energy increases with the square. A velocity. Double your speed and the kinetic energy quadruples. At relativistic speeds, approaching the speed of light, kinetic energy becomes enormous, a single speck of dust, maybe a milligram, hitting at 10% light speed. carries the kinetic energy of several kilograms of TNT. A pebble, a few grams, would hit with the force of a nuclear weapon. The spacecraft would need shielding, heavy, thick shielding at the front to absorb or deflect impacts, but shielding adds mass, which makes the spacecraft harder to accelerate, which requires more fuel or a more powerful engine. You might also use magnetic fields to deflect charged particles, essentially creating an artificial magnetosphere like Earth's. But magnetic fields require power, and they only work on charged particles, not neutral atoms or dust grains. Some designs propose a sacrificial shield, a large disk of material positioned ahead of the spacecraft to take the impacts. If a large object is detected, you could try to maneuver around it, but at 10% light speed, you're covering about 30 million m every second. Detection and course correction would need to happen almost instantaneously. Then there's radiation. Space is filled with cosmic rays, high-energy particles from exploding stars, black holes, and other violent events. Earth's magnetic field and atmosphere protect us from most of this radiation. In deep space, there's no protection. Cosmic rays can damage DNA, increasing cancer risk and causing radiation sickness. The spacecraft hull would provide some shielding, but stopping high-energy cosmic rays requires thick, heavy materials. Again, this adds mass. Some particles are so energetic they'll punch through almost anything. The crew would receive a cumulative radiation dose over 42 years that would be far beyond what's considered safe on Earth. Cancer rates would be elevated. Some crew members would develop tumors, cataracts, and other radiation-related illnesses. There's no way around this with current technology. It's a calculated risk, one that anyone volunteering for such a journey would have to accept. Communication with Earth adds another layer of psychological difficulty. At the start of the journey, radio signals would take only a few minutes to reach Earth. But as the spacecraft travels farther, that delay increases. 1 light year out, messages take 1 year to arrive. 2 light years. 2 years. By the time you're halfway to Alpha Centauri, messages take over 2 years each way. A round-trip conversation takes more than 4 years. You send a message, asking a question. 4 years later, you get an answer. By then, the context has changed. You've probably forgotten what you asked. The people you're talking to might have retired, moved on, or passed away. Communication becomes an exchange of letters across time, not a conversation. News from Earth would arrive years out of date. Political situations, cultural trends, technological advances, all of it would be history by the time you heard about it. The spacecraft crew would be culturally frozen in the year they launched. Earth would move on without them. By the time they arrive at Alpha Centauri, Earth might have changed beyond recognition. The mission that launched them might have been forgotten or abandoned. There might not even be anyone listening for their signals anymore. This isolation is profound. You'd be more alone than any human has ever been. Separated not just by distance, but by time. Cut off from everything and everyone you knew. And then there's the question of what happens when you arrive. After 42 years, you reach Proxima Centauri. Now, what you can't just land on Proxima Centauri B, assuming it's even habitable. The spacecraft is moving at 10% light speed. To enter orbit, you'd need to slow down, which requires just as much energy as speeding up in the first place. If your propulsion system accelerated you to 10% light speed over several years at the start of the journey, you'd need to flip the spacecraft around and decelerate for several more years at the end. This means you'd need twice as much fuel, or you'd need a different deceleration method. One proposal is a magnetic sail. As you approach the target star, you deploy a large loop of superconducting wire, creating a magnetic field. This field interacts with the star's solar wind, charged particles streaming out from the star, creating drag that slows you down. The problem is that solar wind is very weak. Deceleration would be slow, taking years or even decades. And it only works if the target star has a strong solar wind, which red dwarfs like Proxima Centauri don't. Another option is to use the destination star's light. Deploy a light sail and use the star's photons to slow down. Again, this takes time and requires precise orientation, or you could carry extra fuel, but that makes the spacecraft much heavier, which requires more fuel to accelerate, which makes it heavier still. This is the tyranny of the rocket equation. Every kilogram of payload requires multiple kilograms of fuel to move it. If you can't slow down, you're stuck doing a flyby. You scream past Proxima Centauri at enormous speed, taking pictures and measurements for a few hours or days, and then you're gone, flying off into deep space with no way to stop or turn around. All that effort, 42 years of travel, for a brief glimpse. Let's say you do manage to slow down and enter orbit around Proxima Centauri b. What would you find? Proxima Centauri is a red dwarf, much smaller and cooler than the Sun. It's only about 12% the Sun's mass and emits less than 1% of the Sun's light. For a planet to be warm enough for liquid water, it would need to orbit very close, much closer than Earth orbits the Sun. Proxima Centauri b orbits its star every 11.2 days at a distance of only about 4.6 million miles, or 7.5 million kilometers. That's about 5% of the distance from Earth to the Sun. At that distance, the planet is likely tidally locked, meaning one side always faces the star, just like the Moon always shows the same face. To Earth, one hemisphere would be in permanent daylight, the other in permanent darkness. The day side might be scorched, the night side frozen. Any habitable zone would be a narrow ring around the terminator, the boundary between day and night where temperatures might be moderate. But even if conditions are right for liquid water, Proxima Centauri is an active star. It produces powerful flares, sudden bursts of radiation, and charged particles. These flares can be hundreds of times more intense than the Sun's flares. A planet orbiting so close would be bathed in this radiation regularly. Unless the planet has a strong magnetic field to deflect the radiation, the surface would be sterilized. Any life would need to be deep underground or underwater. The atmosphere, if there is one, might be stripped away over time by the stellar wind and flares. So, Proxima Centauri b might not be the welcoming Earth-like world we'd hope for. It might be a radiation-blasted rock with no atmosphere, or a frozen wasteland, or something in between. We won't know. Until we get there. And that's the gamble. You're committing 42 years, possibly your entire life, to reach a destination that might be completely inhospitable. There's no guarantee of success, no way to know in advance if the journey will be worth it. You'd be betting everything on incomplete data and optimistic assumptions. Let's consider the crew's perspective. You volunteer for this mission, knowing you'll spend 4 decades in a metal tube, knowing you'll never return to Earth, knowing you'll age and possibly not see the destination. Why would anyone do this for some? It would be the adventure, the chance to be part of something historic, to be among the first humans to leave the solar system and visit another star. For others, it might be escape, leaving behind problems on Earth for a fresh start. Even if that fresh start is 4 light years away, some might be driven by scientific curiosity, the desire to see what's out there, to answer the question of whether life exists beyond Earth, and some might go because they believe humanity's future depends on becoming an interstellar species spreading to other stars to ensure our survival. But whatever the motivation, the volunteers would be giving up everything: family, friends, careers, the chance to have children who would grow up on Earth. They'd be stepping into a one-way journey with no turning back. Training for such a mission would take years. The crew would need expertise in engineering, medicine, agriculture, physics, chemistry, psychology, and dozens of other fields. They'd need to learn to work together to resolve conflicts, to make decisions by consensus or follow a command structure. They'd undergo simulations, spending months or years in isolation on Earth to see if they can handle the psychological stress. Some would drop out. Others would be cut from the program for medical or psychological reasons. Only the most resilient, adaptable, and skilled individuals would make the final crew, and even they would struggle. The launch would be emotional, saying goodbye to loved ones, knowing you'll never see them again, watching Earth recede in the rear cameras, becoming a blue dot, then just another star, and finally disappearing into the background of space. The first few years might be exciting, the novelty of the mission, the pride of being chosen, the camaraderie of the crew. But after a few years, routine sets in. Every day is the same. Wake up, eat breakfast, work your shift, exercise, eat dinner, maybe some recreation, sleep, repeat, the walls. Close in, the faces around you become too familiar. Small annoyances become major irritations. The smell of recycled air, the hum of machinery, the knowledge that you can't leave, can't go outside, can't see a tree or feel rain. It wears on you. Some people would cope by throwing themselves into work, staying busy to avoid thinking about where they are. Others would turn inward. Meditation, art, writing. Relationships would form, people pairing off for companionship and emotional support. There might be children born on the spacecraft, though that raises complicated ethical questions. Is it fair to bring a child into existence on a spacecraft, knowing they'll spend their entire childhood and possibly their whole life in that environment? Children born on the journey would grow up never having experienced Earth. To them, the spacecraft would be normal. They'd learn about Earth from videos and stories, but it would seem distant, almost mythical. By the time they're adults, they might have no desire to return to a place they've never known. Discipline and governance would be critical. Who's in charge? How are decisions made? What happens if someone breaks the rules, commits a crime, becomes violent or uncooperative on Earth? You have police, courts, prisons. On a spacecraft, options are limited. You can't imprison someone for years without wasting valuable crew resources. Exile isn't possible. There's nowhere to send them. In extreme cases, you might have to confine someone to a small cabin, or even consider euthanasia if they become a danger to others. These are horrific choices. But in a closed environment with no outside help, they might become necessary. Mission planners would need to establish a legal framework, a system of justice that the crew agrees to before launch. As the years pass, technology on Earth would continue to advance. By the time the Alpha Centauri crew is halfway through their journey, 20 years in, Earth might have developed faster propulsion systems. A second mission might launch equipped with newer technology, travelling at 20 or 30% light speed. They'd overtake the first crew, arriving at Alpha Centauri decades earlier. The original crew would spend 42 years travelling only to arrive and find that Earth already has a colony there, established by a later mission that passed them along the way. This is the weight calculation, a real concept in interstellar travel discussions. If technology is improving, is it better to wait and launch later with better technology, or launch now and accept that you might be obsolete by the time you arrive? There's no easy answer. If everyone waits, no one ever goes. But if you go too early, you waste resources on a slow mission that gets overtaken. Now, imagine you're part of that first crew. You're 30 years into a 42-year journey. You've sacrificed everything, spent 3 decades in confinement, and then you receive a message from Earth. They've built a faster ship. It's going to arrive before you. Your mission, your sacrifice, it's all been rendered meaningless. How would you feel? Angry, betrayed, devastated? Or maybe relieved that at least someone will get there, that the goal you've been working toward will be achieved, even if not by you? This is the kind of psychological challenge no amount of training can prepare you for. Let's assume the first crew does arrive and they're the first humans to reach Alpha Centauri. They enter orbit around Proxima Centauri b. They send probes down to the surface, analyze the atmosphere, the geology, search for signs of life. What they find would determine the next phase of the mission. If the planet is habitable or at least survivable with technology, they might attempt to land and establish a colony. This would require equipment they brought with them: habitats, life support systems, tools for mining and manufacturing. They'd need to be self-sufficient, producing their own food, water, and air, repairing and building new equipment as needed. If the planet is inhospitable, they'd have to live in orbit or on a moon. If Proxima Centauri b has any moons, they'd be dependent on the spacecraft indefinitely. In either case, they're stuck. There's no going home. The journey used all their fuel. Even if they could refuel somehow, the return trip would take another 42 years. By then, they'd be over 100 red years old. No one would survive. They'd need to build a new life in the Alpha Centauri system. Knowing Earth is unreachably far away, communication with Earth would continue, but with the 4-year delay, conversations would be slow and frustrating. They'd send reports, images, data back to Earth, and Earth would respond with messages of encouragement, updates on new missions, maybe instructions, but the crew would be fundamentally on their own. And here's a chilling thought. What if something goes wrong on the journey? What if a critical system fails? The life support, the reactor, the food production, the water recycling. If it happens early in the journey, you might be able to turn back. But if it happens halfway or more, you're too far from Earth to return and too far from Alpha Centauri to reach it before the failure kills you. You're stranded in the void. There's no rescue coming. No one can reach you. You'd have to fix the problem with whatever resources you have on board, or it would be the end. The entire crew gone, drifting through interstellar space in a silent spacecraft. Decades later. Another mission might find you, a tomb ship filled with the frozen bodies of the crew, a monument to the risks of interstellar travel. This has happened before, in a sense. Early explorers on Earth faced similar risks. Expeditions to the Arctic, the Antarctic, remote islands. Many disappeared, never to be heard from again. Their fates were sometimes discovered years or centuries later. Interstellar travel would be the same, except the timescales are longer, the distance is greater, and the consequences more absolute. Another scenario. What if the crew discovers something unexpected at Alpha Centauri? Not just a planet, but signs of intelligent life. Ruins of an ancient civilization or active alien technology, or even living aliens. First contact with an extraterrestrial intelligence would be the most significant event in human history. But it would also be terrifying. The crew would be alone, representing all of humanity, making decisions that could affect our entire species. How do you communicate with an alien intelligence? What if they're hostile? The crew would have no weapons capable of defending against an advanced civilization. What if the aliens have technology far beyond ours? The crew's reports back to Earth would take 4 years to arrive. Earth's advice would take another 4 years to return. By then, the situation would have evolved beyond recognition. The crew would have to make first contact decisions on their own with no guidance, no backup, and the fate of humanity potentially hanging on their choices. Or what if they find evidence that life existed but went extinct, a dead world, once teeming with life, now silent? What killed them? Disease, war, environmental collapse, a cosmic disaster. And could the same thing happen to Earth? The psychological impact of such a discovery would be profound. On the other hand, what if they find nothing, no life? Not even microbial, just a barren rock orbiting a red dwarf. After 42 years of travel, all that sacrifice, and the result is nothing. Empty space, lifeless worlds, no answers to the questions that drove the mission. That would be a different kind of devastation, not physical, but existential. The realization that we might be alone, that life might be so rare that even travelling to the nearest star yields nothing. Let's talk about the cost of such a mission. Not just financial, though that's staggering, but the cost in human terms. The crew would be sacrificing their lives. Their families would be losing them, saying goodbye forever. Earth would be investing enormous resources, money, materials, expertise into a mission that offers no immediate benefit and might fail entirely. Is it worth it? That's a question each generation has to answer for itself. Some would say no. The resources spent on an interstellar mission could be used to solve problems on Earth. Poverty, disease, climate change, education. Why spend trillions on sending 100 people to another star when billions on Earth are suffering? Others would argue that exploration is what makes us human. We've always pushed beyond the horizon, seeking new lands, new knowledge, new possibilities. Interstellar travel is the next step in that journey, and if we don't go, if we turn inward and focus only on Earth, we're limiting our potential, possibly dooming ourselves to extinction if a catastrophe strikes our planet. There's also the long-term perspective. Humanity has existed for about 300,000 years. Recorded civilization for about 5,000 years. Our industrial age is only about 250 years old. Space travel has existed for less than 70 years. We're babies in cosmic terms. If humanity survives for another 1,000 years, another 10,000, another million, then a 42-year journey to Alpha Centauri will seem like a small step. Our descendants might look back at the first interstellar missions the way we look back at Columbus or Mellin, as the beginning of something much larger. But we have to take that first step. Someone has to go knowing the risks, accepting the sacrifices, and hoping that what they find makes it worthwhile. Would you go imagine you're offered a position on the crew? All expenses paid. The best training, a place in history. But you'll leave Earth forever. You'll spend the rest of your life in space. You might arrive at a new world, or you might not make it along the way. There's no guarantee. Would you accept? Some people would say yes immediately. The adventure, the legacy, the chance to see another star up close. It would be worth any price. Others would refuse. The thought of leaving Earth, never seeing a natural sky again, never walking on grass or swimming in an ocean is too much to give up, and both answers are valid. There's no right or wrong choice. It's deeply personal. But the fact that we can even have this conversation that interstellar travel is within the realm of theoretical possibility is remarkable. 100 years ago, this would have been pure fantasy. Now it's engineering and physics and economics. We can calculate what it would take. We can design the spacecraft at least on paper. We can estimate the costs and the timelines. It's not easy. It's not happening tomorrow or even in the next few decades. But it's possible. And that means someday someone will go. The terrifying journey to Alpha Centauri will happen. Maybe not in our lifetime, but eventually. And when it does, the people who go will be among the bravest humans who ever lived. They'll be leaving behind everything they know, everyone they love for a destination they might never reach, driven by curiosity and hope and the belief that what's out there is worth finding. Now let's consider the broader implications. If we do establish a presence at Alpha Centauri, what does that mean for humanity? We'd be a 2-star species with populations in both the solar system and the Alpha Centauri system. These populations would be separated by over 4 light years with communication delays of at least 8 years for a round-trip message. They diverge culturally, politically, even biologically over time. Different environments would select for different traits. Lower gravity might favour taller, thinner body types. Higher radiation might favour individuals with better DNA repair mechanisms. Over thousands of years, the populations might become distinct enough that they'd be considered separate subspecies or even species. This is speculative, but it's based on how evolution works. Isolated populations diverge, and 4 light years is about as isolated as you can get. The Alpha Centauri colony would need to be self-sufficient from the start, but they'd also want to maintain ties to Earth. Trade isn't practical. Shipping physical goods between star systems takes decades, but information can be shared. Scientific discoveries, cultural works, technological innovations. All of this could be transmitted via radio or laser communication. Earth benefits from the colony's research and observations. The colony benefits from Earth's larger population and resource base. It's a symbiotic relationship, even if delayed by years. But there's also the potential for conflict. What if the colony wants independence? What if they disagree with Earth's political or economic systems? What if Earth tries to exert control, claiming ownership of the colony because Earth funded the mission? These are questions humanity would have to grapple with. We'd need to establish frameworks for interstellar governance, laws that apply across light years, dispute resolution mechanisms that account for communication delays. It's a new frontier, not just physically, but legally, politically, and socially. There's also the question of follow-up missions. Once the first crew arrives, would Earth send a second wave of colonists, more supplies, updated technology, or would the colony be left to fend for itself, a distant outpost that Earth gradually forgets about? The answer would depend on what the first crew finds. If Proxima Centauri b is habitable and rich in resources, Earth would have strong incentive to send more missions, establishing a larger, more permanent presence. If the planet is marginal or hostile, the colony might remain small, a scientific outpost rather than a true settlement. And there's the possibility of expansion beyond Alpha Centauri. Once you've proven that interstellar travel is possible, once you've established a colony at another star, the next step is to go farther. From Alpha Centauri, you could launch missions to other nearby stars. Barnard's star, 6 light-years away, Wolf 3597.9 light-years. Land 211,185 8.3 light-years. Each of these stars has planets or at least is suspected to. Each could be a potential home for humanity. Over centuries, we could spread through the local neighborhood of the Milky Way, establishing colonies at dozens or hundreds of stars. Each colony would be independent, separated from the others by vast distances, but connected by radio signals and shared heritage. Humanity would become a true interstellar civilization, no longer confined to one star, no longer vulnerable to a single catastrophic event wiping us out. But this is all long-term speculation. The first step is Alpha Centauri, and that first step is terrifying. It's a journey that tests the limits of technology, psychology, and human endurance. It requires sacrifices most people can't imagine. It offers no guarantees, no certainty of success. But it's also inspiring. The idea that we could reach beyond our solar system, that we could visit another star, that we could find new worlds and possibly even new life. It captures the imagination in a way few other endeavors can. It's the ultimate exploration, the final frontier, the culmination of millions of years of evolution that produced a species capable of leaving its home star. And when it happens, when the first humans set foot in another star system, it will be one of the greatest moments in history, not just human history, but the history of life on Earth. For billions of years, life has been confined to this one planet. With interstellar travel, we break that confinement. We become something new, a species that spans the stars. Tonight, we've explored what it would really take to get to Alpha Centauri. We've looked at the distances, the technologies, the challenges, the psychological toll, the risks, and the potential rewards. We've confronted the terrifying reality that such a journey is by any measure one of the most difficult things humanity could attempt. It's not just a matter of building a spacecraft and pointing it at another star. It's decades of travel in a confined environment with no escape, no resupply, and no guarantee of survival. It's isolation on a scale we've never experienced. Separation from Earth by distances that make real-time communication impossible. It's the knowledge that you're leaving everything behind. Everyone you know. Every place you've ever been for a destination you've only seen as a point of light in the sky. And yet, despite all of this, despite the fear and the difficulty and the unknown, there will be people who volunteer. There will be engineers who dedicate their lives to designing the spacecraft. There will be scientists who spend careers figuring out the propulsion, the life support, the navigation. There will be crew members who step aboard that spacecraft, strap themselves in, and launch into the void, knowing they might never return. Because that's what humans do. We explore. We push boundaries. We ask, what's over the next hill, across the next ocean, around the next star? And we go find out. The journey to Alpha Centauri is terrifying, but it's also inevitable. Someday we will go, and when we do, those travellers will carry with them the hopes and dreams of everyone who ever looked up at the night sky and wondered what's out there. They'll be our ambassadors to the cosmos, representing the best of what humanity can be. Courage, curiosity, determination, and hope. The nearest star is 4.24 light-years away, 25 trillion miles of empty space, filled with radiation and dust, and the cold vacuum of the void. Getting there will take everything we have. It will demand technology we haven't yet developed, courage we haven't yet tested, and sacrifices we haven't yet made. But we'll do it. Not tomorrow, not next year, but someday. And when that day comes, when the first spacecraft leaves the solar system bound for Alpha Centauri, it will mark the beginning of humanity's greatest adventure, the journey to the stars. Thank you for joining me tonight on this exploration of what it would take to reach our nearest stellar neighbour. If you found this journey as fascinating and unsettling as I did, please take a moment to like this video and subscribe to the channel. It helps more than you know. And remember, the next time you look up at the night sky and see Alpha Centauri, a faint point of light in the southern sky, you'll know what it would really take to get there. The distance, the danger, the sacrifice, and maybe, just maybe, you'll understand why we'll go anyway. Sleep well tonight, knowing that somewhere out there, 4 light years away, is another star. Possibly with planets, possibly with life. And someday, we're going to find out. But before we end tonight's journey, there's more we need to understand about what makes this trip so uniquely challenging. Let's dig deeper into some of the specific obstacles that would turn a journey to Alpha Centauri into one of the most harrowing experiences imaginable. Start with navigation. You might think pointing a spacecraft at Alpha Centauri and firing the engines would be straightforward. It's not. Space is 3-dimensional, constantly moving, and navigation at interstellar distances requires precision we've never attempted before. Alpha Centauri appears stationary in our sky, but that's an illusion. Every star in the galaxy is moving, orbiting the galactic center at different speeds and in different directions. Our Sun is moving through space at about 500,000 pHa, or about 800,000 km/hour, relative to the cosmic microwave background. Alpha Centauri is moving at a different velocity in a different direction. This means the target isn't where it appears to be. By the time light from Alpha Centauri reaches us, showing us where it was 4 years ago, the star has moved. You need to calculate where it will be when you arrive, 42 years in the future, and aim for that position. This is called leading the target, like shooting at a moving object, except this target is moving through 3-dimensional space at hundreds of thousands of miles per hour. And you're also moving, and both of you are being influenced by the gravity of other stars, the galactic center and dark matter we can't even see. The calculations are phenomenally complex. A tiny error in your initial trajectory, even a fraction of a degree, compounds over years and light years until you miss your target by millions of miles. You'd need constant course corrections throughout the journey, tiny burns of the engines to adjust your path. But here's the problem. Those engines need fuel. Every course correction uses fuel you can't replace. If you run out halfway through the journey, you're stuck on whatever path you're on. You might miss Alpha Centauri entirely, flying past it into deep space with no way to turn around, and navigation requires instruments, telescopes to track your position relative to known stars, accelerometers to measure your velocity, gyroscopes to maintain orientation. All of this equipment needs to work perfectly for decades. If a telescope's mirror gets damaged by a micrometeorite impact, your ability to navigate accurately degrades. If a gyroscope fails, you might not know which direction you're facing. Redundancy is essential, but every backup system adds weight. There's also the problem of relativity. We've talked about time dilation, but there's another effect called relativistic beaming. As you approach significant fractions of light speed, the light from stars ahead of you shifts toward blue wavelengths, while stars behind you shift toward red. This is Doppler shift, the same effect that makes a police siren sound higher, pitched as it approaches and lower as it recedes. At 10% light speed, the Doppler shift is noticeable. Alpha Centauri, which appears yellow from Earth, would start to look bluer as you approach. Stars behind you would This affects navigation because the stars you're using as reference points don't look the way they do from Earth. Your star charts become less reliable. You need to account for relativistic effects in your calculations, adding another layer of complexity. Now, let's talk about the spacecraft. Structure itself, at 10% light speed, the stresses on the ship are immense. Any acceleration or deceleration creates g-forces that the structure needs to withstand. If you accelerate too quickly, the ship could tear itself apart. Imagine a spacecraft several hundred meters long. The engines are at one end pushing. The rest of the ship is pulled along by that thrust. The connection points between sections experience enormous forces. If a joint is weak, if a weld has a microscopic flaw, it could fail and sections of the ship could separate. Material science becomes critical. You need materials that are strong but light. Titanium alloys, carbon fiber composites, advanced ceramics. Every component needs to be tested beyond normal limits because there's no room for failure. One structural failure could doom the entire mission. And then there's thermal expansion and contraction. In space, temperatures vary wildly. The side of the ship facing the direction of travel might be bombarded by high-energy particles and dust, generating heat. The side facing away radiates heat into the coldness of space. This creates temperature gradients across the structure. Materials expand when heated and contract when cooled. If different parts of the ship are at different temperatures, they expand and contract at different rates. Over time, this can cause stress fractures, warping, misalignment of critical components. Engineers would need to design the ship with thermal management in mind, heat pipes to distribute warmth evenly, insulation to protect sensitive areas, radiators to shed excess heat. All of this adds complexity and weight. The rotating sections that provide artificial gravity create their own challenges. Rotation generates centrifugal force, but it also creates stress on the structure. The outer hull experiences constant outward pressure. Imagine a spinning cylinder. The faster it spins, the more force pushes outward, trying to tear it apart. This is why the rotation rate has to be carefully controlled. Too fast and the structure fails. Too slow and the artificial gravity is too weak. And if the rotation is uneven, if one section spins faster than another, you get wobbling. This wobble can amplify over time, becoming more and more severe until the whole ship is tumbling out of control. Stabilization systems, gyroscopes, and reaction wheels would be needed to maintain smooth rotation. But these systems require power and maintenance. Let's discuss the human factor more deeply. We've touched on psychological challenges, but the reality is even more complex. Humans are social creatures evolved to live in communities with variety and change. The spacecraft environment is the opposite. The same people, the same spaces, the same routines for decades. Studies of isolated groups like those in Antarctic research stations or submarines show predictable patterns. In the first few weeks or months, everyone is excited, cooperative, motivated. This is called the honeymoon phase. Then reality sets in, the novelty wears off. Irritations begin. Small habits that seemed quirky at first become infuriating. The way someone chews their food, a laugh that's too loud, someone who talks too much or not enough. These annoyances build up, creating tension. This is the conflict phase, and it can last months or years. Arguments break out over trivial things. Cliques form. People stop communicating except when necessary. The social fabric of the crew starts to fray. In isolation studies on Earth, this is when people drop out, request, transfers, or have mental breakdowns. But on an interstellar spacecraft, there's no dropping out, no transfer, no escape. You have to find a way through it. Eventually, if the crew survives the conflict phase, they might reach acceptance. This is when people make peace with their situation. They accept the limitations, adjust their expectations, and find ways to coexist. But not everyone reaches this phase. Some people never adjust. They remain angry, depressed, or withdrawn for the duration. Mission planners would need to screen for psychological resilience. But there's no perfect test. You can't simulate 42 years of confinement. The best you can do is approximate it with shorter isolation periods and hope that predicts who will cope and who won't. Relationships and intimacy add another layer. People will form romantic relationships. This is natural and probably healthy, providing emotional support and comfort. But relationships also bring complications, jealousy, breakups, love triangles. What happens when a relationship ends badly and the two people still have to work together every day for decades? What if they both want to avoid each other? But the ship is so small, there's no way to do that. And what about reproduction? If people are having sexual relationships, pregnancies are likely. Birth control can fail. Even with the most reliable methods, over 42 years and a crew of 100, you'd probably have some unplanned pregnancies. Pregnancy and childbirth in space present medical challenges. We don't fully understand how microgravity or even artificial gravity affects fetal development. Studies on animals suggest there could be issues with bone formation, muscle development, and organ placement. Human pregnancies have never been attempted in space, so we don't know what to expect. And even if the pregnancy goes smoothly, raising a child on a spacecraft is a profound ethical question. That child didn't choose to be on this journey. They'll grow up in a confined space, never experiencing Earth. Is that fair to them? Some would argue it's not, that bringing children into such an environment is cruel. Others would say life is precious wherever it occurs and children could bring joy and hope to the crew. There's no easy answer. Mission planners would need to establish policies. Are pregnancies allowed, encouraged, forbidden if a pregnancy occurs? Is abortion an option? These are deeply personal questions with no universal right answer. But they'd need to be addressed before launch. Education would be critical. If children are born on the ship, they need to be educated. Not just basic reading and math, but engineering, medicine, science. They'd need to be trained to maintain the ship and contribute to the mission. The crew would essentially be running a school alongside everything else. Cultural preservation becomes important too. The crew would bring music, books, films, art from Earth. These cultural artifacts help maintain a connection to home, remind people of where they came from. But over time, the crew would create their own culture, new art, new music, new stories based on their unique experience. They develop their own traditions, holidays, rituals. By the time they arrive at Alpha Centauri, they might have a culture that's distinct from Earth, a blend of what they brought and what they created along the way. Language might even evolve over 42 years, especially if children are being raised on the ship. Language could drift. New words would be invented for spacecraft-specific concepts. Old words might fall out of use. Slang would develop. By the end of the journey, the crew might speak a dialect that's difficult for people on Earth to understand. Now, let's consider the possibility of something going catastrophically wrong. Not just a system failure, but a complete disaster. A reactor breach flooding the ship with radiation. A collision with a larger object that punches through the hull, causing rapid decompression. A fire in the life support section, destroying the equipment that produces oxygen. Any of these scenarios would be fatal. The crew would have minutes to hours before it's over for everyone. There's no rescue, no way to call for help that would arrive in time. They'd have to solve the problem themselves or perish. Let's walk through a scenario. Imagine a micrometeorite impact. A grain of sand-sized object travelling at 10% light speed from the opposite direction. Relative velocity is 20% light speed. The kinetic energy is enormous. It punches through the forward shield, through the outer hull and into the habitat section. The impact creates a hole the size of a dinner plate. Air rushes out, pressure drops, alarms scream, the crew has seconds to react, emergency protocols kick in, airtight doors slam shut, sealing off the breached section. This saves most of the ship, but anyone in the breached section is cut off. If they're not wearing suits, they have about 15 seconds of useful consciousness before hypoxia sets in. The rest of the crew scrambles. They need to assess the damage. Figure out which section is breached. Determine if it can be repaired. If the breach is in a critical area, like the life support system, the entire mission is at risk. They'd need to jury-rig a repair, patch the hole from the inside or outside. This requires someone to go EVA, extravehicular activity, putting on a spacesuit and going outside the ship. But remember, the ship is travelling at 10% light speed. The cosmic ray flux outside is intense. Any EVA exposes the person to lethal radiation doses. They might complete the repair and save the ship, but they'd be sacrificing their own future. Cancer within months, radiation, sickness, a slow, painful decline. Someone would have to volunteer knowing they're sacrificing themselves to save everyone else. That's the kind of impossible choice that could arise. Or consider a different scenario, a pathogen outbreak. Despite all the screening and quarantine procedures before launch, a virus or bacteria makes it on board. Maybe it was dormant in someone's body, activated by stress or radiation. Maybe it mutated in the unique environment of the spacecraft. It starts spreading. People get sick, fever, coughing, weakness. The medical team tries to contain it, isolate the infected, treat symptoms, develop a cure or vaccine, but medical resources are limited. If the pathogen is aggressive, if it spreads faster than they can control, it could wipe out the entire crew. And even if they contain it, they might have to make terrible decisions. Quarantine the infected in a sealed section with no treatment, letting nature take its course to prevent the disease from spreading. Euthanize someone who's infected and suffering with no hope of recovery. These are nightmare scenarios, but they're realistic possibilities. Interstellar travel doesn't just test your technology, it tests your humanity. It forces you to confront situations where there are no good options, only varying degrees of bad, and you have to live with the consequences of your choices for the rest of the journey. Let's shift to thinking about what arrival at Alpha Centauri would actually be like. You've spent 42 years travelling. You're exhausted, aged, scarred by the journey, but you made it. Alpha Centauri grows larger in the viewports, no longer a point of light, but a visible disk. You're still months away from the closest approach, but the anticipation builds. You start detailed observations. Telescopes focus on Proxima Centauri b, the planet you've come to explore. You measure its size, mass, orbital characteristics. You analyze the spectrum of light reflecting off it, looking for signs of an atmosphere, water vapor, oxygen, methane. These signatures would tell you if the planet is habitable or if it's a dead rock. The data comes in. Proxima Centauri b is indeed rocky, slightly larger than Earth. There's an atmosphere, mostly carbon dioxide and nitrogen, no free oxygen, which means no photosynthetic life-producing oxygen, at least not in large quantities. Surface temperature measurements show extreme variation. The day side is blistering hot, over 300 degrees C or 572 degrees F. The night side is frozen, below 00 degrees C or minus 48 degrees F. The habitable zone, if it exists, would be a narrow band around the terminator. Further analysis shows the planet is indeed tidally locked. One face always toward the star. The atmospheric circulation is bizarre. Hot air rises on the day side, flows high in the atmosphere to the night side, cools and sinks, then flows back along the surface. This creates permanent hurricane force. Winds at the terminator, the boundary between day and night. Landing there would be challenging. And then there's the radiation. Proxima Centauri is an active star. You detect flares, sudden bursts of X-rays and charged particles. These flares happen every few days, bombarding the planet with radiation. Without a strong magnetic field, the surface is being sterilized regularly. Any life would need to be deep underground or in subsurface oceans. The crew debates, is it worth landing on such a hostile world? Would it be better to stay in orbit, send down robotic probes, and conduct research from the safety of the ship? But after 42 years, the temptation to set foot on another world is overwhelming. A landing team is assembled. They'll descend in a shuttle, land in the Terminator zone, set up a temporary habitat, and explore. The descent is tense. The shuttle fights against the winds buffeted by gusts that threaten to flip it over. The pilot, trained for decades for this moment, manages to land safely. The team disembarks, stepping onto the surface of Proxima Centauri b, the first humans to set foot on a world beyond the solar system. They're wearing heavy suits designed to protect against the radiation and the temperature extremes. The sky is alien. The star Proxima Centauri hangs on the horizon, a deep red, much dimmer than the sun. It casts an eerie red light over the landscape. The terrain is rocky, barren, no vegetation, no obvious signs of life. But there's something strange. Patterns. In the rock, layers that suggest sedimentary deposition. This rock was formed underwater. There was liquid water here maybe millions of years ago before the star's flares stripped away the atmosphere and boiled the oceans. The team takes samples, drills into the ground, searches for fossils, any evidence of past life, and then they find it. A layer of rock rich in organic compounds, chemical signatures consistent with biological processes. Not life now, but life that existed long ago. Proxima Centauri b was once a living world. And then something happened. The star's activity increased, the radiation intensified, and life was extinguished. This discovery is monumental proof that life can arise on other worlds, but also a sobering reminder of how fragile it is. If Earth's sun were as active as Proxima Centauri, life on Earth might never have developed, or it might have been wiped out before it could evolve intelligence. We got lucky. Our sun is calm, stable, and Earth has a magnetic field that protects us. Proxima Centauri b had neither of those advantages. The crew sends the data back to Earth, a signal that will take 4 years to arrive. Meanwhile, they establish a permanent presence. They build habitats, set up mining equipment to extract resources from the planet, begin manufacturing fuel and supplies. The goal is to make the Alpha Centauri outpost self-sufficient. And they start thinking about the next step. Other stars, other worlds. From Alpha Centauri, the nearest stars are different than from Earth. Barnard's star is closer from here than it is from the solar system. The crew could, in theory, continue the journey, but they're old, tired. Most of the original crew who launched from Earth are in their 70s or 80s. Some have passed along the way. The next generation, those who were children when the mission launched or were born on the ship, they're the ones who might continue. They've never known Earth. To them, Alpha Centauri is home. The idea of spending another few decades travelling to yet another star might not appeal, or maybe it does. Maybe the urge to explore, to see what's beyond the next horizon is part of who they are. This is how humanity spreads. One star at a time. Each colony becomes a stepping stone to the next. Over centuries, we could establish a network of outposts throughout the local region of the galaxy, each separated by light years, each independent, but connected by radio signals and shared knowledge. It's a slow process measured in human lifetimes and generations, but it's the only way, unless we develop faster than light travel, which current physics says is impossible. This is the reality of interstellar expansion. Slow, dangerous, and utterly transformative. Now, let's bring it back to Earth and think about what this mission means for those who stayed behind. You're on Earth watching the launch of the Alpha Centauri mission. It's a global event. Billions of people watch as the spacecraft lifts off, beginning its journey to another star. There's excitement, pride, hope. Humanity is taking its first step toward the stars. But there's also sadness. The crew members have families, friends, loved ones who are saying goodbye forever. They'll never see each other again. Messages can be sent, but with years of delay, it's not the same as a real conversation. Years pass. The spacecraft sends back updates. Everything is going well. The crew is healthy. Systems are functioning. Earth celebrates each milestone. 1 year out, 5 years, 10 years. But as time goes on, interest wanes. The mission becomes background news. People move on with their lives. The crew becomes a distant memory, a footnote in history. And then 42 years after launch, a message arrives from Alpha Centauri. They made it. They're in orbit around Proxima Centauri b. They're preparing to land. Earth erupts in celebration. The mission succeeded. Humanity has reached another star. But the people who sent the mission are mostly gone. The engineers who designed the spacecraft are retired or gone. The politicians who funded it are out of office. The children who watched the launch are now in their 40s or 50s with children of their own. The world has changed. New technologies have been developed. Faster propulsion systems are on the drawing board. In another decade or two, Earth might send a second mission that could reach Alpha Centauri in half the time. The first crew's journey, their sacrifice, already feels outdated. And yet, they were first. They proved it could be done. They opened the door for everyone who comes after. That's their legacy. The messages continue. The crew sends back data, images, discoveries. The finding of ancient life on Proxima Centauri b is a revelation. It changes how we see the universe, how we think about our place in it. We're not alone in having life. Even if that life is extinct, the universe is or was full of living worlds. And if life arose on Proxima Centauri b, it probably arose on countless other worlds, too. Some of those worlds might still have life. Some might have intelligent life. The crew at Alpha Centauri starts thinking about that. They point their telescopes at other stars, looking for signs, radio signals, laser pulses, anything that might indicate technology. They find nothing. The galaxy, as far as they can tell, is silent. Either we're alone or everyone else is too far away, or they're not broadcasting, or they've gone extinct like the life on Proxima Centauri b. The silence is both disappointing and humbling. Back on Earth, society continues to evolve. The existence of the Alpha Centauri colony raises questions. Do they have the same rights as Eartha? Can they declare independence? What if there's a conflict between Earth and the colony? With a 4-year communication delay, there's no way to have a meaningful negotiation. By the time Earth sends a message and receives a reply, 8 years have passed. Situations can change drastically in that time. Philosophers, lawyers, and politicians debate these issues. New frameworks for interstellar governance are proposed. Some suggest each colony should be fully autonomous, making its own decisions. Others argue Earth should retain ultimate authority since Earth funded and launched the missions. There's no consensus, but the conversation is happening. Humanity is grappling with what it means to be a multi-star civilization. Meanwhile, technology marches on. The breakthrough everyone hoped for doesn't come. We don't discover warp drives or wormholes. Physics still limits us to slower than light travel, but propulsion improves. New engine designs push speeds to 15%, 20% of light speed. The second wave of missions to Alpha Centauri and other stars are faster, safer, more efficient. They build on the lessons learned from the first mission, and eventually, decades after the first landing, Earth sends a colony ship. Not a small crew of explorers, but hundreds or thousands of people intent on establishing a permanent large-scale settlement. This ship carries the equipment to terraform, to build cities, to create a true second home for humanity. The original crew, those who are still alive, welcome the newcomers, their elders now, respected for their pioneering journey. They watch as the colony grows, as children run through newly built streets, as farms are established and industry develops. Alpha Centauri transforms from a distant star into a thriving human world, and the process repeats. From Alpha Centauri, missions are launched to other stars. The wave of human expansion ripples outward slowly but inexorably. This is the long-term vision, not just reaching Alpha Centauri, but using it as a base for further exploration. Each new colony becomes a launching point for the next. Over centuries and millennia, humanity spreads through the galaxy, star by star, world by world. It's a vision that requires patience, sacrifice, and an acceptance of time scales far longer than individual human lives. But it's the vision that drives those who look at the stars and see not just lights in the sky, but destinations, homes, futures. Let's consider one final aspect of this journey now, the philosophy of it. Why go it? All if the journey is so dangerous, so difficult, so terrifying. Why attempt it? What drives the human urge to explore? Part of it is curiosity. We want to know what's out there. Is there life? What are other worlds like? Can we survive beyond Earth? These questions have no answers unless we go and look. Part of it is survival. Earth won't last forever. In about 5 billion years, the Sun will expand into a red giant engulfing the inner planets. Earth will be destroyed long before that, perhaps in 1 billion years. The Sun will get hot enough that Earth's oceans will boil away. Life as we know it will end. If humanity is still around, we'll need somewhere else to go. Spreading to other stars ensures that even if Earth is destroyed, humanity survives. Part of it is the challenge. Humans are at our best when we're solving difficult problems, pushing boundaries, achieving things that seem impossible. Interstellar travel is the ultimate challenge. It requires us to innovate, to cooperate, to think beyond ourselves. And part of it is legacy. We want to leave something behind, to know that we mattered, that we contributed to something greater than ourselves. The crew of an interstellar mission is leaving a legacy that will endure for centuries. They're making it possible for future generations to live among the stars. That's a powerful motivator. But there's also a darker side. The journey to Alpha Centauri would be terrifying, not just because of the physical dangers, but because of the existential ones. You'd be confronting the reality of your own insignificance. You're a tiny speck on a tiny ship in an unimaginably vast universe. You're leaving behind everything that gave your life meaning, your family, your culture, your world for an uncertain future. You'd have to come to terms with the fact that you might fail, that you might not make it along the way, that your sacrifice might be for nothing. That's a level of existential dread most people never have to face. And yet, some people would embrace it. They'd see it as an opportunity to confront the fundamental questions of existence. What does it mean to be human? What is our purpose? Are we significant or insignificant? The journey would force you to grapple with these questions in a way that's impossible in the comfortable confines of Earth. And maybe that's part of the appeal. Not despite the terror, but because of it. The journey strips away all the distractions, all the comforts, all the illusions we use to avoid confronting the big questions. It leaves you alone with the universe, with yourself, with the raw reality of existence. And in that confrontation, you might find something meaning purpose, a deeper understanding of who you are and what you're capable of. Or you might find nothing, just the cold, indifferent void. Either way, you'd know. You'd have looked into the abyss and survived or not. That's what makes the journey to Alpha Centauri terrifying. It's not just the risk of not making it, it's the risk of confronting the ultimate questions and discovering answers you're not prepared for. It's the risk of finding out that we're alone, that the universe is empty, that there's no grand purpose, no meaning beyond what we create for ourselves, or the risk of finding life, intelligence, and discovering that we're not special, that our existence is just one among countless others, no more significant than any other. Both possibilities are frightening in their own way, and yet we'll go because the alternative, staying on Earth and never knowing, is even more frightening. We're a species that needs to know, that can't help but explore, that pushes forward into the unknown despite the risks. That's what makes us human. That's what will carry us to Alpha Centauri and beyond. But before we say goodnight, there's one more dimension to this journey that deserves our attention. The technological hurdles we'd need to overcome before such a mission could even launch. We've talked about propulsion systems, but let's be more specific about what each option really involves and why none of them are ready for a mission like this. Chemical rockets, the kind we use today to launch satellites and reach the Moon and Mars, are completely inadequate for the interstellar travel. They work by combining fuel and oxidizer in a combustion chamber. The chemical reaction produces hot gases that expand rapidly and are expelled out the back of the rocket, creating thrust. This is efficient enough to get off Earth and even reach other planets in our solar system. But the energy density is too low for interstellar speeds. The fastest speed achieved by a chemical rocket, the Apollo 10 capsule, during its return from the Moon was about 25,000 mph. or about 40,000 km/h. That's fast enough to circle Earth in less than an hour. But to reach Alpha Centauri at that speed would take over 100,000 years. We need something with far higher energy density. Nuclear propulsion offers better performance. There are several types. Nuclear thermal rockets heat a propellant, usually hydrogen, using a nuclear reactor. The hot hydrogen is expelled through a nozzle, creating thrust. This gives you about twice the efficiency of chemical rockets. Better, but still nowhere near enough for interstellar travel. Then there's nuclear pulse propulsion, which we mentioned earlier. Project Orion studied in the 1950s, and 60S proposed using nuclear bombs. You drop a bomb behind your spacecraft, detonate it and absorb the blast with a massive shock absorber. Plate. Each explosion would give you a push. Do this thousands of times and you could reach several percent of light speed. The engineering is terrifying. The shock absorber plate would need to be incredibly strong to withstand repeated nuclear explosions. It would need to be enormous, maybe 100 m in diameter or more. The spacecraft behind the plate would need to be protected from radiation and heat. The nuclear weapons themselves would need to be reliable. If one fails to detonate, you've wasted mass and fuel. If one detonates prematurely or too close, it could destroy the shock plate and the ship. And politically, launching thousands of nuclear weapons into space, even for a scientific mission, would be nearly impossible. The Partial Test Ban Treaty of 1963 banned nuclear weapons tests in space. Getting international agreement to exempt an Orion-style spacecraft would require decades of negotiation and might never happen. Project Orion was shelved not because the physics was wrong, but because the politics and practicality made it impossible. Fusion propulsion is more promising in theory. Fusion is what powers the sun. Two hydrogen atoms, usually deuterium and tritium, combine to form helium, releasing energy. The energy released per unit mass is far greater than chemical reactions or fission. If you could sustain a controlled fusion reaction in a rocket engine, you could achieve much higher exhaust velocities, meaning better efficiency and higher speeds. But controlled fusion is hard, really hard. The challenge is that fusion requires temperatures of millions of degrees and pressures that are difficult to achieve and maintain. On the Sun, the immense gravity provides the pressure. On Earth, we need to create that pressure artificially. There are two main approaches. Magnetic confinement, where you use powerful magnetic fields to contain a plasma at fusion temperatures. This is the basis of designs like TOCACs and stellarators, or inertial confinement, where you compress a fuel pellet using lasers or other means until fusion occurs. After 70 years of research and billions of dollars in funding, we've achieved fusion reactions in laboratories. But we haven't achieved net positive energy output. The energy needed to create the conditions for fusion exceeds the energy released by the fusion reaction. We're close. Experiments like ITER, the International Thermonuclear Experimental Reactor being built in France, might achieve net positive fusion in the coming decades. But going from a laboratory reactor that produces net energy to a compact, reliable fusion rocket engine that can operate continuously for years or decades is another enormous step. It's not impossible, but it's not something we'll have in the next few decades. Maybe by the end of this century, if research progresses well and funding continues, antimatter propulsion is even further out of reach. Antimatter annihilation is the most energy-dense reaction possible. When a particle meets its antiparticle, both are completely converted to energy. The efficiency is 100%. Compare that to fusion, which converts less than 1% of the mass to energy, or chemical reactions, which convert a tiny fraction of a percent. If you had antimatter fuel, You could achieve incredible speeds with relatively small amounts. A few kilograms of antimatter could accelerate a spacecraft to a significant fraction of light speed. The problem is production. Antimatter doesn't exist naturally on Earth. It's produced in particle accelerators by smashing high-energy particles together. Occasionally, an antiparticle is created. You can capture it using magnetic fields and store it in a magnetic trap. But the production rate is infinitesimally slow. It takes billions of particle collisions to produce a single antiroton. The total amount of antimatter ever produced on Earth is less than 20 nanog. That's 20 billionths of a gram. Barely enough to power a light bulb for a few seconds. To fuel an interstellar spacecraft, you'd need kilog or tons of antimatter. At current production rates, it would take billions of years to accumulate that much, and the cost would be astronomical. Producing a single gram of antimatter with current technology would cost trillions of dollars. We'd need revolutionary advances in production methods, perhaps a dedicated antimatter factory in space using solar power, or a fusion reactor to run massive particle accelerators. Even then, you'd need to store the antimatter. It can't touch any normal matter or it annihilates instantly. You'd need perfect magnetic containment, with redundant systems and backup power. Any failure even for a fraction of a second and your entire fuel supply explodes. The energy release would be catastrophic. A single kilogram of antimatter annihilating releases energy equivalent to 43 megatons of TNT. That's roughly the yield of the largest nuclear bomb ever tested, the Tsar bomber. If your containment fails, your spacecraft becomes a fireball visible across light years. So antimatter propulsion, while theoretically possible, is practically out of reach for the foreseeable future. Ion drives are real and operational, but they're slow. They work by ionizing a propellant, usually xenon gas, and accelerating the ions using electric fields. The exhaust velocity is very high, much higher than chemical rockets, which makes them efficient, but the thrust is tiny. An ion drive produces about as much force as a piece of paper resting on your hand. It takes weeks or months to build up any significant speed. For missions within the solar system, this is fine. You have time. You can run the engine for years, gradually accelerating and eventually reach high speeds. NASA's Dawn mission used ion drives to visit the asteroids Vesta and Ceres. It worked beautifully. But for interstellar travel, you need more thrust. Even running an ion drive continuously for decades, you'd only reach a small fraction of a percent of light speed. Not fast enough. You could scale up the ion drive and just make it more powerful, but that requires more electricity. A more powerful ion drive needs mega or gigawatt of power. That means larger nuclear reactors, which means more mass, which means you need even more thrust to accelerate that mass. It becomes a vicious cycle. Solar sails avoid the need for carrying fuel. Instead, they use light pressure. Photons from the sun carry momentum. When they reflect off a mirror, they transfer that momentum, producing a tiny push. Build a sail large enough and light enough, and you can accelerate using sunlight alone. No fuel, no engines, just a giant reflective sheet. The problem is that sunlight is weak. At Earth's distance from the sun, light pressure is about 9 millionths of a Newton per square meter. To get useful acceleration, you need a sail that's square kilm in area, but weighs only a few G per square meter. That's thinner than tissue paper, but also strong enough to withstand the stresses of acceleration and not tear materials. Science hasn't achieved this yet. We can make thin reflective films, but they're either too heavy or too fragile. And even if you solve the materials problem, the sun's light weakens rapidly as you move away from it. By the time you're a few AU out past the orbit of Mars, The light pressure is so weak that acceleration becomes negligible. You'd need a different light source. This is where laser propulsion comes in. Instead of relying on sunlight, you build a massive laser array on Earth or in orbit. You point it at the spacecraft sail and blast it with concentrated light. The laser can be much more powerful than sunlight, accelerating the sail to high speeds. The Breakthrough Starshot project envisions exactly this: a ground-based laser array with a total power of 100 GeV. That's the output of 100 large power plants. This array would beam light at a tiny spacecraft, maybe a gram in mass, with a sail a few meters across. The laser would push the sail for a few minutes, accelerating it to 20% light speed. Then the laser shuts off and the spacecraft coasts the rest of the way to Alpha Centauri. Sounds great, but there are challenges. First, the laser array would cost tens of billions of dollars to build. Second, you need to keep the laser focused on a tiny sail that's accelerating away from Earth at thousands of kilometers. The precision required is staggering. Any misalignment and the laser beam misses the sail entirely. You'd need adaptive optics systems that adjust the beam in real time to compensate for atmospheric turbulence if the laser is ground-based or orbital perturbations if it's space-based. Third, the spacecraft is so small that it can't carry much. A few cameras, maybe a basic spectrometer, a transmitter, that's it. You're not sending humans, you're sending a probe that will do a flyby. Snap a few pictures and transmit them back to Earth. And transmission is another problem. With such a small spacecraft, the transmitter's power is limited, maybe a few watts at most. The signal would be incredibly weak by the time it reaches Earth. 4 light years away, you'd need enormous receiving dishes on Earth to detect it, and the data rate would be slow. It might take months or years to transmit a single high-resolution image. Still, Breakthrough Starshot is the most realistic near-term proposal for reaching Alpha Centauri. Even if it's only with a tiny probe, if it works, we could have images of Proxima Centauri b within a few decades. That would be historic. But it's not the same as sending humans. For a crewed mission, we need better technology systems that don't exist yet. We need propulsion that can accelerate a large spacecraft, hundreds or thousands of tons to a significant fraction of light speed. We need life support that can sustain people for decades with minimal resupply. We need radiation shielding that actually works against cosmic rays. We need medical technology that can handle any illness or injury that might occur. We need psychological support systems that can keep people sane in isolation for 40 years. None of this is ready. All of it is theoretically possible. But turning theory into practice takes time, money, and effort. Decades at minimum, possibly centuries, and that's assuming steady progress, no major setbacks, and continued funding. Let's talk about funding. Interstellar missions are expensive. Estimates for a crewed mission to Alpha Centauri range from hundreds of billions to trillions of dollars. That's comparable to or greater than the entire GDP of some countries. Who pays for this? Governments could fund it, but convincing taxpayers to spend trillions on a mission that won't return results for decades is politically difficult, especially when there are pressing needs on Earth: poverty, disease, climate change, infrastructure. Private companies might contribute, but the return on investment is unclear. There's no profit in sending people to Alpha Centauri, no resources to extract and bring back, no products to sell. It's pure exploration and science. Some billionaires are interested in space exploration for its own sake. Elon Musk with SpaceX and Mars, Jeff Bezos with Blue Origin, they might fund or partially fund an interstellar mission as a legacy project. But even their resources, vast as they are, might not be enough for a project this large. International cooperation is probably necessary. A coalition of countries pooling resources like the International Space Station. But on a much larger scale, the ISS cost about $150 billion over several decades, shared among the US, Russia, Europe, Japan, and Canada. An interstellar mission would cost many times more, but it's possible. If humanity decides this is a priority, if we can set aside national rivalries and work together, we could do it. The question is whether we have the will. And there's another factor, time. The people who decide to fund and launch the mission won't live to see the results. Politicians think in terms of election cycles, a few years at most. Corporations think in terms of quarterly earnings. An interstellar mission requires thinking in terms of lifetimes and generations. That's a hard sell, but maybe as climate change and resource depletion make Earth's future more uncertain, people will become more interested in ensuring humanity's survival by spreading to other stars. Maybe the existential threat will provide the motivation that pure curiosity doesn't. It's a grim reason to go, but it might be the one that actually drives us. Now, let's consider the ethical dimensions. Is it right to send people on a journey this dangerous even with volunteers who understand the risks? Are we as a society obligated to ensure their safety to a reasonable degree? What level of risk is acceptable on Earth? We have regulations for dangerous jobs. Miners, firefighters, astronauts, all work in hazardous environments. But there are safety standards, backup systems, rescue protocols. For an interstellar mission, rescue is impossible. Once the spacecraft leaves the solar system, they're on their own. If something goes wrong, it's over. No one can help them. Is it ethical to put people in that situation? Some would argue yes. People take risks all the time. Mountaineers climb Everest knowing they might not return. Test pilots fly experimental aircraft. Explorers venture into remote wilderness, as long as the risks are explained and the volunteers consent. It's their choice. Others would say no. We have a moral obligation to protect people, even from their own risky decisions. Sending someone on a journey with a high probability they won't return, even if they volunteer, is ethically questionable. There's no easy answer. It depends on your values, your view of individual autonomy versus collective responsibility. Then there's the question of what we owe to any life we might find. If Proxima Centauri b has microbial life or had it in the past, do we have a right to land there and potentially contaminate it with Earth microbes? We've already grappled with this in our solar system. Planetary protection protocols are designed to prevent Earth life from hitching a ride on our spacecraft and contaminating Mars or Europa or other worlds where life might exist. We sterilize spacecraft, use, clean rooms, follow strict procedures. For an interstellar mission, the stakes are even higher. If we find a world with life, even simple life, it's a scientific treasure. Contaminating it with Earth organisms could compromise our ability to study it to determine if it arose independently or shares a common origin with Earth life. We'd need even stricter protocols. Maybe the crew wouldn't be allowed to land at all. Only robotic probes that have been thoroughly sterilized. Or maybe we decide that the potential for contamination is worth the risk, that the value of human exploration outweighs the risk to alien microbes. Again, there's no universally right answer. It's a decision future generations will have to make, balancing scientific integrity, human curiosity, and ethical responsibility. And then there's the question of what we'd do if we found intelligent life. The probability is low. Most estimates suggest intelligent, technologically advanced civilizations are extremely rare. But if we did encounter one, what? Then first contact would be the most significant event in human history. It would change everything, our understanding of ourselves, our place in the universe, our religions, our philosophies. All of it would be challenged. The Alpha Centauri crew would be humanity's representatives. The decisions they make, the messages they send could shape our relationship with this alien civilization for centuries. Do they attempt communication? What do they say? Do they reveal Earth's location? That could be dangerous if the aliens are hostile or expansionist. Do they try to learn the aliens' language, their culture, their technology, or do they observe from a distance, gathering data but not making direct contact? These are decisions that should ideally be made by all of humanity collectively. But with a 4-year communication delay each way, there's no time for a global debate. The crew would have to decide in the moment based on their training, their judgment, and their conscience. That's a terrifying responsibility. The stakes couldn't be higher. A wrong move could start a war, provoke an invasion, or squander a unique opportunity for cooperation and learning. And even if the encounter is peaceful, there are complications. If the aliens have advanced technology far beyond ours, should we try to acquire it? Learning their technology could leapfrog our own development, solving problems that might take us centuries to solve on our own. But it could also make us dependent on them or reveal information they don't want to share, creating conflict. And if we learn their technology, do we share it with Earth or do we keep it at Alpha Centauri, creating a technological imbalance between the colony and Earth that could lead to political tensions, resentment, even conflict between Earth and its first interstellar colony? These are scenarios that seem like science fiction. But if we're seriously planning interstellar missions, we need to think about them. We need protocols, guidelines, decision-making frameworks. We can't just send people into the unknown and hope they figure it out. Of course. The most likely scenario is that we find nothing. No life, no intelligence, no alien civilizations, just empty worlds orbiting distant stars. That's what most of our solar system is. Barren rock, ice, and gas. There's no reason to think the rest of the galaxy is any different. But even finding nothing has value. It tells us something about the universe. It suggests that life is rare, that Earth is special, that we have a unique responsibility to preserve and protect the life we have. And it means that as we spread to other stars, we're not displacing anyone, we're filling an empty niche, bringing life to worlds that have never known it. That's its own kind of significance. Let's return to the human experience one more time. Imagine you're part of the crew 10 years into the journey. You've adjusted to life on the spacecraft. The initial excitement has faded. The routines are familiar, almost comforting. You know every corridor, every room, every face. You've had your share of conflicts and reconciliations. You formed close friendships, maybe a romantic relationship. You found ways to occupy your time, hobbies, studies, work. But there are moments, quiet moments, when you're alone, when the weight of what you've done hits you. You're never going home. Earth is a point of light behind you, indistinguishable from any other star. Everyone you knew, everyone you loved, they're all gone. Not dead. Not yet, but gone from your life. Moving forward through time without you. You'll never see them again. You'll never walk on Earth again. Never feel rain. Never smell fresh air. Never see a tree or hear a bird. All of that is behind you. Irretrievably lost. And ahead of you is only more of the same. More corridors. More recycled air, more of the same faces for decades. And then, If you're lucky, you'll arrive at a world that might be hostile, barren, nothing like Earth. In those moments, you might question your decision. You might feel regret, sorrow, even despair. Why did you volunteer? What were you thinking? Was it worth it? But then you remember. You remember the reasons you went. The curiosity, the adventure, the desire to be part of something larger than yourself. You remember that you're doing something no one has ever done before. You're traveling to another star. You're expanding the boundaries of human experience, and you're part of history, and you find meaning in that. You push the doubt away and focus on the mission, on the goal. You're not just surviving the journey, you're contributing to humanity's future. Every day you spend on this ship, every problem you solve, every piece of data you collect, it's all part of the mission. It all matters, and that gives you purpose. That gets you through the hard moments. The crew would develop rituals, traditions, ways of marking time and creating meaning, anniversaries of the launch, birthdays, both Earth birthdays and ship birthdays, the day you boarded, holidays from Earth cultures, celebrated and adapted to the spacecraft environment, maybe new holidays invented just for the crew, naming days for children born on the ship, remembrance ceremonies for those who pass along the way. These rituals would help create a sense of community, a shared culture that binds the crew together. And they'd tell stories, stories of Earth passed down to younger crew members who've never seen it, stories of the launch, the training, the early days of the mission, stories invented on the ship, myths and legends that reflect the crew's experiences. Over time, these stories would become the foundation of a unique culture, neither fully Earth nor fully something else, but a blend, a new identity forged in the crucible of interstellar space. By the time the crew reaches Alpha Centauri, they might not think of themselves as Earthlings anymore. They might be something new, star travelers, pioneers, the first of a new branch of humanity. And that transformation, that evolution, of identity is part of what makes the journey terrifying. You're not just travelling through space. You're travelling away from who you were toward who you'll become. And you don't know what that will be until you get there. Now, as we finally approach the end of our journey tonight, let's take a step back and look at the big picture. The journey to Alpha Centauri is more than a technical challenge. It's a test of everything we are as a species, our ingenuity, our courage, our ability to work together toward a common goal. It's a statement about our values, about what we think is important, about what we're willing to sacrifice for knowledge and exploration. And it's a gamble, a bet that the universe is worth exploring, that what we'll find out there, whether it's life, resources, knowledge, or simply the achievement itself, is worth the cost in time, money, and human lives. We don't know if that bet will pay off. We won't know until we go. But the very act of making the bet, of committing to such an audacious goal, says something profound about us. It says we're not content to stay in one place. We're not satisfied with the familiar and the safe. We need to push boundaries to see what's beyond the horizon. Even if the horizon is 4 light years away, that drive, that restlessness, that curiosity, it's what makes us human. It's what drove our ancestors out of Africa to populate every continent on Earth. It's what drove us to cross oceans, to climb mountains, to explore the poles, to land on the moon, and it's what will drive us to the stars. The journey to Alpha Centauri is terrifying, but it's also inevitable. Someday someone will make that journey, and when they do, They'll carry with them the hopes and dreams of all of us who looked up at the stars and wondered. Thank you for joining me tonight on this deep exploration of what it would really take to reach Alpha Centauri, our nearest stellar neighbour. We've looked at the distances, the technologies, the human challenges, the risks, the potential rewards, and the philosophical questions that such a journey raises. If this exploration moved you, challenged you, or made you think differently about humanity's future in space, please take a moment to like this video and subscribe to the channel. Your support helps me continue making these deep dives into the cosmos and our place in it. And remember, the next time you look up at the night sky, if you're in the southern hemisphere, you can see Alpha Centauri, a bright point of light, deceptively peaceful, hiding the immense challenge it represents. 4.224 light-years away, 25 trillion miles of empty, hostile space. A journey that would test the limits of our technology, our endurance, and our humanity. A journey that's terrifying in its scope, its dangers, and its implications. But also a journey that's calling to us, beckoning us forward, daring us to take that next great step. Sleep well tonight, knowing that somewhere in the cosmos, perhaps sooner than we think, that journey will begin, and when it does, it will mark the moment when humanity truly became an interstellar species. Good night, and may your dreams reach for the stars.